So in the last video, we discussed about the method of solving a differential equation. The first method was separation of variable, okay? So the separation of variable method is used if the differential equation is separable, meaning that if the differential equation is dy over dx equals to some function, and then if the right hand side function can be written as the product of a function of x and function of y, then in that case you can make 1 over function of y times dy equals to function of x times dx that way, okay? So you can basically separate the variables, right? So and then you integrate after that. We did some examples. So and you see that the also in the 6.1 we discussed about exponential model, that is dn over dt equals to r times n, right? And you see that if you solve this, how did we solve this? We use the separation of variables here, right? How did we do that? To solve this, we just divide by n on both sides, and then t it will look like 1 over n dn equals to r dt, right? You see that this is separated, n all the n's are here, all the non-n's are here, r is a constant, so r and dt, and then you integrate, that's what you will get. Okay, and you use the initial condition, and sub 0 is the initial value of the population. That's what we did, right? So if you graph this function, then it will look like this. So t is here, n is here, suppose n0, the initial population is here, and if you graph this equation for r positive, then this is what it looks like. Okay, so meaning that when t tends to infinity, when t increases, then the value of n, the population, will increase and increase. So it keeps increasing, meaning that for a longer time this will go to the population size become infinity. The population will be bigger and bigger and bigger and bigger and bigger, right? So but in reality that is not correct, because the population does not grow indefinitely, right? So because the population growth depends on so many other things. For example, the availability of the food or the resources, right? If a region or if a place has enough food for a certain number of individuals, then the growth of the population will grow up to that level that has enough food. Then after that it will start to decline, right? Or the growth slows down once the population reaches close to the carrying capacity. So what is the carrying capacity? Carrying capacity is the total resources available to sustain a certain number of population, right? Certain population, okay? So if you want to take account into that, meaning that if there is a limited resources, then the differential equation dn over dt equals to rn will be changed like dn over dt equals to rn times 1 minus n over k, where r is the growth rate, like we have r here, growth rate, right? And k is the carrying capacity. Now you see that what is happening here is, if k is bigger than n, if k is bigger than n, then n over k will be positive, right? Sorry, n over k is less than 1, right? If k is bigger, then n over k is less than 1. At that time 1 minus less than 1 will be positive, meaning that we are assuming that r is positive, okay? So in that case, if k is bigger than n, then n divided by k will be less than 1. So 1 minus less than 1 will be positive, so the right hand side will be positive, so meaning that it will grow. But when n grows and grows and grows and grows, so when n is close to k or n is equals to k, what happens? If n is equals to k, then n over k will be 1. So 1 minus 1 will be 0. So the right hand side will be 0, meaning that the population, the rate of change is 0, meaning the population does not change. The population stays the same, okay? But if k is less, if the initial population is bigger, if n is bigger than k, then this quantity will be bigger than 1, right? So 1 minus bigger than 1 will be negative. So the right hand side will be negative. At that time dn over dt will be negative. That means the rate of change is negative, means the population declines, okay? Meaning that if you start with the more population, then the available resources, the population decline. If you start with the exact same number of people that has available resources, enough for the available resources for that many people, then the population stays the same. But if you start with the smaller population, but there are the resources are enough for a bigger number of people or bigger population, then the dn over dt will be positive, so the growth rate or the population increase, right? So this equation is called logistic equation. Okay, so logistic equation. Now, so how do we solve this logistic equation? Because you see that there is n and then nk, so basically it looks like we can solve using the separation of variables, right? How do I do that? Let us do that. You can do 1 over n, okay? You can do 1 over n times 1 minus n over k, and then dn. So r and k are constant values. They are just like a number, like 5, 10, like that, right? Equals to what is left. So I am dividing by n times 1 minus n over k, and then separating the variable, and then equals to r times dt. That's what I got. Okay. Now you see that these are separated. So I want to integrate on both sides. But before integration, what I want to do is I want to make the same denominator here and then move that k there. So what do you get? You will get k over n times k minus n dn equals to r dt. You see that? Now what we do next is we integrate on both sides. Okay. So before we do the exact integration, let me write down integral of, so you can write 1 over k minus n plus 1 over you can write n, right? And then dn equals to rt, okay, plus c. You can write like that. Okay. So what is the integral here then? So the integral look like, what is the integral of 1 over k minus n? That will be natural log of, but that will be negative, okay? Because you see that what is the derivative of k minus n with respect to n? It will be negative 1, right? But there is positive 1. So what will that be? It will be like negative natural log of k minus n. Let me write down the absolute value there, k minus n, and then plus natural log of n, okay, equals to rt plus c. Okay, if you combine that, you will get what? You will get natural log of n, right, minus natural log of k minus n, okay, equals to kt plus c. Okay, guys. So what I want to do here is, let me write down, I want to let us multiply both sides by negative sign, because I want to write this on the top when I merge this, okay? Let us multiply by the negative sign. What do you get? You get natural log of k minus n, and then, you know what, I should have done this in this. Let me do that thing. Let me multiply by the negative sign on this step, okay? So I want to multiply by the negative sign on this step. What do I get? Natural log of k minus n minus natural log of n, okay? N is positive, that's why I was not writing the absolute value there, but negative rt minus c. You see that? So if you combine those two log, you will get natural log of k minus n over n, right? You see that? So that will be what? Negative rt minus c. So if you take the natural log out, then you will get, if you get rid of the natural log, then you can write k minus n over n equals to e to the negative c, negative rt, right? Rt minus c. You see that? So e to the negative rt minus c. That's what you get. Now what I'm going to do is I'm going to solve for n here. Okay, guys, I want to solve for n. So how do I solve for n? Let us do that. So you have k over n minus 1 is equals to, let us write down that as e to the negative kt times e to the negative c. So e to the negative c is a constant, so let us write down that as b. Okay, let's write down that as b. So what do you get? K over n equals to 1 plus b e to the negative kt, right? So what will be n then? So there is 1 in the denominator, right? So what can you write on this? So you can write that, therefore you can do the cross multiplication, you can solve for n. Therefore nt, that n is basically nt, equals to k over 1 plus b e to the negative kt. That is the solution of the logistic equation. Okay guys, so you see that if there is a carrying capacity for the population growth, then we use the logistic equation, right? Logistic differential equation. That is the logistic differential equation. That's what it is, right? And the solution of the logistic differential equation is nt equals to k over 1 plus b e to the negative kt. That's what the solution look like. Okay guys, so this is the solution of the logistic equation. So where k is the carrying capacity, b is a constant, and then k is so not k, I'm sorry, why did I write k? That should be r, right? Not k, that should be r. And then you see that e to the negative r, right? Not k, and that is r. Okay, that is r, not k. Okay, because you see that e to the negative rt minus c, e to the negative rt, e to the negative c, I denoted that by b. Okay, so it is basically, if you add 1 on both sides, right here, if you add 1 on both sides, you get 1 plus b e to the negative rt. Okay, therefore if you solve for n, you just move this to the down and move n to the right side, right? It's just the cross multiplication there. If you do that, then nt will be k over k divided by that thing, right? 1 plus b e to the negative rt. So k is the carrying capacity, and then r is the growth rate. Okay guys, so I want to do one example. Okay, so this example is almost it is like example number 62 from your book. Okay, so it is similar to that. Okay guys, so let me write down the question. That is the example is, suppose that at t equals to 0, there were 2 grams of bacteria, and then 3 hours later the bacteria grows, and then there were 4 grams. The maximum weight of the culture, so that means that there is enough space, or the food for the bacteria is culture is 20 grams. That is the carrying capacity, right? 20 grams. Okay, so number A, the question number A is, write the logistic equation. This is the logistic equation, right? Logistic equation. So we call this as the logistic equation. This is the logistic differential equation. Logistic differential equation, right? Differential equation. And this is the solution. So that is the logistic equation. Okay. So write the logistic equation. That models the bacterial weight, right? Bacterial weight. So second question is, find the bacterial weight after 5 hours. Number C is, when will the culture or bacterial weight, that's the same thing, okay, become 15 grams. That's question number C. And question number D is, write a logistic differential equation. Now write the logistic differential equation, and then use Euler's method. You know Euler's method, right? method with step size, h equals to 1. Okay, to solve says write the logistic differential equation that models the growth rate of the culture's weight. So you want to model the growth rate of the culture's weight. Okay, so you want to do dy over dt, that's the rate of change, right? So you want to find out dy over dt for that. Okay, and you want to write for t equals to 0 what is the exact value, because exact value will be obtained from part A. Okay, and then the approximate value will be obtained from part D, that is the logistic, we are solving that by logistic differential equation. Okay, step size to I would say to estimate. Okay, to estimate the bacterial growth, to estimate bacterial weight. Okay, and number E is what time the culture weight or bacterial weight increase most rapidly. Number E is what time the bacterial growth increase rapidly. That is the last question. Okay guys, so let us do number A. So first of all, let us list what are the given things here on this example. Okay, let us first list the given things. So at t equals to 0, 2 grams of bacteria. Let's say n at 0 equals to 2, and after 3 hours it is 4 grams. N at 3 equals to 4 grams. The maximum weight of the culture is 20 grams. So K is equal to, that is the carrying capacity. Okay, 20 grams. So these are the given things. Let us do number A now. So that is the given thing. Okay, so let me write solution here. Solution. I listed the given thing. Now I want to answer question number A. It says write the logistic equation. This is logistic equation. Okay, logistic equation that models the bacterial growth. So what is that formula? We have the formula as nt equals to k over 1 plus b e to the minus rt, right? That is what we have, right? So now we plug in the values of k and then just k, right? And then we'll find out the values of r and b using these information, which is same as 20 over 1 plus b e to the negative rt. That's what we got, right? And then using n0 equals to 2, what do you get? You get 2 equals to, I'm doing t equals to 0, you will get 20 over 1 plus b. You see that? So what do you get? This implies 2 plus 2b equals to 20, right? So this implies, what do you get from here? This implies b equals to what? 20 minus 2 is 18, so b equals to 9. That's what I get, right? Now I will use b equals to 9 here and then use n3 equals to 4. Also using n at 3 equals to 4, what do you get? 4 equals to k is 20 over 1 plus b is 9 times e to the negative r, and then t is what? 3, right? Because at t equals to 3 the n is 4. That's what we are using, right? So now what we need to do is we need to solve this. Okay, so let us solve the value. So if you do that, you will get so there is a 1 and then you do 20 equals to 4 plus 36 e to the negative 3r. Okay, now subtract 4, what do you get? So if you subtract 4, 16 equals to 36 e to the negative 3r. Okay, so what do you get then? So you get 16 over 36. Let's do that. We get 16 over 36 equals to e to the negative 3r, okay? And then take natural log, you get negative 3r equals to natural log of 16 over 36. So r equals to negative 1/3 natural log of 16 over 36. If you use, 36, okay? So if you use calculator for negative 1/3 times natural log of 16 over 36, you will get r is almost equal to 0.27. That's what you get. That is the value of r, okay? That is part A. Let us do part B there. So let me do part B. So part B, okay, I want to do it here for part B. So part B is saying that find the bacterial weight after 5 hours. So what is the equation here? So basically we got n equals to 20 over, the final equation for A is 1 plus 9 e to the negative 0.27t. That's what the final model look like after you plug in the value of R and B, right? That's what you got, right? So now what I want to do is, the question is asking n at 5 equals to what? You just replace t by 5 here on this equation, right? So therefore n at 5 is equals to 20 over 1 plus 9 e to the negative 0.27, and then t is 5. So if you use calculator for this, you will get n equals to 6. That's what you get. Okay guys, so number 3, part 3 is, when will the culture become 15 grams? So it is asking, when will the culture become 15 grams? Okay, that's what the question C is asking. So number C, so for what t n of n t equals to 15, that's what it is asking. Okay, so we will solve for t by replacing n equals to, this n is 15, so you write 15 equals to 20 over 1 plus 9 e to the negative 0.27 t. That's what you do, right? And then you just multiply on both sides. So I mean, just do the cross multiplication, right? You do 20 equals to 15 plus 135 e to the negative 0.27 t, right? So you just subtract, so you just subtract 15, you will get 5 equals to 135 e to the negative 0.27 t, divide by 135, divide by 135, divide by 135, that will cancel out. So you get e to the negative 0.27 t equals to 5 over 135 is how much? So that is 20, that is a 27, 1 over 27, that's what you get. Okay, so now take the natural log, you get negative 0.27 t equals to natural log of 1 over 27. So t is negative 1 over 0.27, natural log of 1 over 27. If you use calculator, you will get 12.19 hours. So this is the time that that it takes for the bacteria to grow to 15 grams. Okay guys, so the next thing we want to do is part D. In part D, you want to use the Weightless method. So first of all, write the logistic differential equation. So what will be the logistic differential equation? It will be dy over, let me use different color for that. So it will be dy over dt. So dy over dt, okay, is equals to what? So you get, so dy over dt is, r is what? What was our r? 0.27, right? 0.27, and then it's not y, n, right? So dn over dt, because we have denoted by n. So dn over dt equals to, dn over dt equals 0.27 times n, and then 1 minus n over, what was k? K is 20. So that is the differential equation. Now what you want to do is, you want to solve this equation by by the you want to solve this equation by the Euler's method. Okay, guys. So how do I do that? Is to solve by the Euler's method, we need the table, right? We need I here, and then you do Ti. Okay, we have given h equals to 1. Okay, Ti, and then we do Ni. Okay, and then this is function, right? This is a function of Ti comma Ni. This is given as 0.27 n, okay, times 1 minus Ni. Let's do Ni over 20. That's what you will do. Okay, guys. So for I, this is I. Okay, this is I. So for I equals to 0, what is given? For I equals to 0, t equals to, so I equals to 0, it will be t0, right? What is the value of t0? T0 is 0, it is given, right? Time 0 is 0. At that time, the population is 2. At t0 is 0, the population is 2, right? So at time equals to 0, the population is 2. So what is the value of f of ti and I? So you just replace that 0.27 times n0, because I is 0, right? N0 is 2, and then 1 minus 2 over 20. Find out that value. Okay, similarly, so after we find out how much would that be, let me find out that. So 0.27 times 2, and then times 1 minus 2 over 20. That's what I got. Okay, that is the right answer. 0.486. That's what I got. 0.486. That's what I got. Okay, so now when I equals to 1, so t1 will be what? Ti. What is the formula for ti? Ti equals to t0 plus n times I, right? That is the formula to find out the ti. So if t for I equals to 1, you will get t0 plus ti is nh. Let's do that, not I. nh. So ti is t0 plus I times h, not nh. I times h. That is the formula, right? Because if you go back to and watch the Euler's method video, that's what the formula is. So when I equals to 1, then it is t1 will be t0 is 0 plus I times h. I is 1, h is also 1, so it will be 1. Okay, when t1 equals to 1, what will be the ni then? So what you need to do here is ni is given as what? So what is the formula for the Euler's method? Yn plus 1 equals to yn plus h times f of t n y n. That's what the formula is, right? Because there was x and y, so x, but here it is t and y. I'm assuming t and y, or you can write n, no problem, it's the same, just the generic formula, right? So what you need to do is you need to do n, this is n0 equals to, so what will be n1? N1 will be, you just replace n by 0. What do you get? Y1 is same as n1, right? So y0, that is 2 plus, let me erase this a little bit because I don't have enough space there. Okay, so you will get 2 plus, and then h is 1 times that 0.486. That's what you get. Okay, so and then some number after that. So that value is basically 2.486. That's what you get. That is the n1 value. Okay, guys, and then using that, using t1 and n1, you just plug in here. That will be, so f of t1 and 1 will be how much? Because this is f of t0 y0 n0, so f of t and y1 will be 0.27 times 2 times 1 minus 2 over 20. Not 2, 2.486. No, oh, this should not be 2. It should be 2.486, and this is 2.486, and find out that. Okay, so if you continue this way, these are the values you will get. At 2, you will get 3.075. So T1 will be, T2 will be 2. So that value will be, N2 will be 3.075. At 3, T3 will be 3, N3 will be 3.778. 3.778. At 4, T4 equals to 4, and then N4 is equals to 4.607, and so on. Okay, so this is how you find out. So let us do part E of the question. It says what time the bacterial growth increased rapidly. Okay, so you see that if you graph the solution of this graph, okay, if you graph this one, then you will get the graph of that solution will look like this, you know. So it will look like N0 will be here, N0, it will increase, so K will be here, okay, it will increase and then it start to slow down. Okay, see that? This is how the graph look like. Okay, so this is like 20, not 20, so that one, the other one is 20, so this is like K equals to 20. That's what the graph looks like for this problem. Okay, N0 is 2, so this is basically N0 is 2. Okay, this is 2. It starts from 2 and then it goes to 20. That's what the graph looks like. Okay, now the question is, so for how long the growth is rapid? Because you see that for some time the growth is rapid and then they start to slow down the growth. Okay, so how do I figure that out? Is, let us first write down the differential equation. So we have dn over dt is equals to 0.27, okay, and then times n times 1 minus n over 20. That's what you got, right? If you simplify the right hand side, you will get this 0.27 and then n minus 0.27 n square over 20. Okay, so if you plot, because you see that the right hand side is a quadratic function in n, okay, and then the n squared term has the negative exponent. So if you plot, like if you draw a plot for this is like dn over dt versus n, so how does this look like is this one. Okay, so you will see that the right hand side plot is the plot of the right hand side. Okay, the right hand side plot will look like this, because it has n square and n term, there is no constant term, it will pass through the origin, it will go up like this and then start to go down. Okay, so dn over dt is 0 at n equals to 0 and it is 0 at n equals to 20. That's what you get. You see that? And the rate of change is positive. Okay, the rate of change is positive between 0 and 20 because the dn over dt is above, because the dn over dt is that right hand side function, right? This right hand side function is that graph between 0 and 20. The graph is above n axis, meaning that the rate of change will be positive there. But you see that until half, the rate of change is increasing, and then after that the rate of change is decreasing. Again, the rate of change can be increasing or decreasing, but you see that the rate of change is positive here. So between 0 and 20 the rate of change is positive. Okay, so it is increasing everywhere, but the increasing is fast for the first middle half, meaning that when the population is half of the 20 is, so this is k equals to 20, right? So k over 2 is equals to 10. When the population is until the population reaches 10, because we started from 2, right? Until the population reaches 10, then the rate of change is increasing. Rate of change is increasing, meaning that the population is increasing rapidly. So you can write the population increases rapidly until the population, until it reaches 10. It reaches 10. You see that? Now, how to find out the time? To find for how long it increases rapidly. That's what the question is saying, right? To find the time, you see, like we did like a question number C. Okay, we solve 10 equals to 20 over 1 plus 9 e to the negative 0.27t. So how do I solve that? Again, do the same thing, right? So you do, so cross multiplication, you get 20 equals to 10 plus 90 e to the negative 0.27t, and solve that. So subtract 10, you will get 10 equals to 90 times e to the negative 0.27t, right? And then you get divide by 90. What do you get? Divide by 90, divide by 90. Okay, so 10 over 90 equals to e to the negative 0.27t. Now take the log, you get this, t equals to, okay, if you take the log, this is what you get, t equals to negative 1 over 0.27, and the natural log of 10 over 90, or 1 over 9, you can write the same thing. So you will get 8 point something, okay, 8.13 or something like that, okay, if you do that. So that is the time when the population increases rapidly. Okay guys, so this is how we do the problem related to the rate of change, the logistic equation. Okay, all right guys, okay, thank you.